Ever looked up at the sun and just felt its warmth? It feels peaceful, doesn't it? But our star is anything but quiet. It's a raging, chaotic ball of plasma, constantly blasting a storm of charged particles out into space in every direction. This storm is called the solar wind. It travels at mind-boggling speeds, sometimes over 1,000,000 miles per hour, and it fills our entire solar system. This wind is what creates the beautiful aurora on Earth, but it can also threaten our satellites and power grids. For decades, we've known the solar wind exists, but there's a huge, glaring mystery at its heart. How does it get so incredibly fast? Think about it this way. The surface of the sun, the part we can see, is about 10,000 degrees Fahrenheit. But as you move away from the surface into its atmosphere, the corona, the temperature skyrockets to millions of degrees. It's like walking away from a bonfire and suddenly feeling hotter instead of cooler. It completely defies our everyday logic. This extreme heat is what's believed to give the solar wind its initial, powerful push, accelerating particles to escape the sun's immense gravity. But the how and why of this coronal heating has been one of the biggest unsolved puzzles in astrophysics. How does the sun's energy travel from its surface, bypass the cooler layers, and superheat the outer atmosphere to such an extreme degree? That's the core of the solar wind enigma. Scientists have had theories. Of course, for a long time, the leading idea involved something called nanoflares. Imagine tiny, scaled-down versions of the giant solar flares we see erupting from the sun. The theory was that millions of these nanoflares are constantly popping off all over the corona, too small and numerous to see individually, but collectively releasing enough energy to heat the whole atmosphere to millions of degrees. It's a bit like a huge stadium full of people all striking a match at once. One match is nothing, but millions together create a massive amount of heat and light. This seemed like a plausible explanation, a constant, simmering release of energy. Another major theory focuses on magnetic waves, specifically something called alpha waves. The sun has an incredibly complex and powerful magnetic field. Imagine these magnetic field lines like guitar strings. The churning, boiling motion on the sun's surface is constantly plucking these strings, sending vibrations or waves rippling outwards into the corona. The theory goes that these waves carry enormous amounts of energy. As they travel up into the less dense corona, they can break like an ocean wave crashing on the shore and deposit all their energy as heat, accelerating the surrounding particles into the solar wind. So, is it countless tiny explosions, or is it vibrating magnetic waves? For decades, we could only speculate from afar. We needed to get closer, much, much closer. And that's where our hero enters the story, NASA's Parker Solar Probe. This is, without a doubt, one of the most audacious missions humanity has ever undertaken. The goal? To touch the sun. Launched in 2018, Parker is designed to fly directly through the sun's corona, the very birthplace of the solar wind, enduring temperatures and radiation that would vaporize any previous spacecraft. Its heat shield, a marvel of engineering, has to withstand temperatures of nearly 2,500 degrees Fahrenheit while keeping the instruments behind it at a comfortable room temperature. This isn't just an incremental step, it's a giant leap into the unknown, a journey into the belly of the beast to solve this long-standing mystery once and for all. As Parker's solar probe began its daring orbits, getting closer to the sun with each pass, it started sending back data that was nothing short of revolutionary. And what it found has begun to rewrite our understanding. The probe detected something incredible inside the solar wind: powerful, rogue magnetic structures. Scientists have nicknamed them switchbacks. Picture the solar wind flowing out from the sun in a relatively straight line. Suddenly, for a few seconds or even minutes, the magnetic field will flip back on itself, like a Z-shaped kink in a rope, before snapping back into place. These switchbacks are not gentle ripples. They are events where the solar wind particles are suddenly and violently accelerated. Given an extra kick, the probe flew directly through these switchbacks, measuring the particles and magnetic fields inside them. And the data confirmed it. These kinks in the magnetic field were acting like accelerators, slinging particles outwards at incredible speeds. The discovery was huge. We weren't just observing the result of the acceleration anymore. We were flying through the very mechanism that was causing it. But this just opened up another question. What was creating these switchbacks in the first place? Were they related to the nanoflares or the alpha waves? The mystery deepened. The answer, it seems, lies at the very source. As Parker got even closer to the Sun, flying just a few million miles above its surface, it was able to connect the switchbacks it was flying through with events happening on the Sun's surface. The data suggests that these switchbacks originate low in the solar atmosphere, in the footpoints of where magnetic field lines emerge from the Sun's surface. At these points, the magnetic field lines can sometimes cross and reconnect in an explosive event, a process called magnetic reconnection. Think of two magnetic loops coming together, snapping, and reconfiguring into a new shape. This explosive reconnection event not only releases a burst of energy, much like a nanoflare, but it also creates the S-shaped kink that then propagates outwards into space as a switchback. So, it appears the answer isn't one or the other. It's not just nanoflares, and it's not just waves. It's a beautiful, complex interplay of both. Magnetic reconnection events at the Sun's surface, which act like nanoflares, create these alphenic waves and switchbacks that then travel outwards, heating the corona and accelerating the solar wind. We're finally seeing the complete chain of events, from the Sun's bubbling surface all the way out into the solar system. Parker's solar probe has essentially followed the energy from its source and watched it kick the solar wind into high gear. What does this mean for us, back here on Earth? Understanding the solar wind isn't just an academic exercise. This stream of particles is what drives space weather. A powerful gust of solar wind can compress Earth's magnetic shield, induce currents in our power grids causing blackouts, disrupt GPS and communication satellites, and even pose a radiation risk to astronauts. By understanding exactly how the solar wind is accelerated, we can build better models to predict its arrival and intensity. This is like learning to forecast hurricanes, but for space. It gives us the lead time we need to protect our vital technology and infrastructure from the Sun's temper tantrums. The journey of Parker's solar probe is far from over. It will continue to fly closer and closer to the Sun, venturing into regions no one has ever explored, gathering more data to refine these incredible new discoveries. We stand at the cusp of finally solving a puzzle that has perplexed scientists for generations. The Sun, our life-giving star, is slowly giving up its secrets. And with each piece of data sent back from this brave little probe, we gain a deeper, more intimate understanding of the powerful forces that shape our solar system and our very existence within it. Thank you so much for joining me on this deep dive into the solar wind enigma. It's truly an exciting time in space exploration. If you found this fascinating, please hit that like button and consider subscribing for more stories from the frontiers of science. We'd love to have you as part of our community. Until next time, stay curious.